everyone. Hi. So today we will talk about something really interesting, and so although some of you may have already learned the concept, but we will present the concept in a way I'm pretty confident that is quite kind of just novel, and we will also discuss a very important underlying mathematical principle. The principle is so important that it's not actually only applicable to math, but just applicable to nearly all sciences. So the concept we will talk about is integers. That will include both positive integers, which are just 0, 1, from 0, starting from 0, 1, 2, 3, 4. Those non-zero natural numbers are called positive integers, but we will also talk about negative integers. And negative integers, 0, and the positive integers altogether are called integers. Not surprising. So that's the important concept we'll talk about. I'm pretty sure that some of you have already learned this and even know how to do basic arithmetical operations like subtraction, addition with integers. But as you have already seen previously, we took a very rigorous approach to introduce the concept of numbers or natural numbers and properly define what are those arithmetical operations like subtraction, addition, multiplication means. And we will do exactly the same to introduce integers. But why are we taking this approach? So we must recall what kind of problems we discussed last time. So let's review what we discussed last time. We know that when we do subtraction, we introduce this operation decrement, which is essentially just the inverse of increment. So decrement is nothing new if we really understand what increment means. However, because our increment operation was defined from a starting point, which was 0, and from that point on, we increment to introduce all the natural numbers. So when we do decrement, let's just say from A, we can do decrement to 7, then decrement to 6, and so on. Then all the way down to 0. But at that point, we cannot do further decrement. Why? Because there was no increment resulting in 0. That's one of our axioms when we try to introduce the concept of natural numbers. So this really creates a big problem. Why? Because we know if we don't have a decrement operation goes beyond 0, we cannot do subtractions like 8 subtract 13. Because if you want to take 13 away from 8, you try to do 13 times of decrement. That's how we define subtraction, right? It's just repeatedly subtracting 1, which is equivalent to repeatedly decrement 1. So how do we solve this problem? This is what we want to have, right? Conceptually, we have only defined all the numbers to the right of 0. Even if you don't have any idea about negative numbers, you can imagine this should be what the number line looks like. because to the left of 0, we should have a symmetrical copy of all the positive, just natural numbers. 1, 2, 3, 4. If this is a mirror image, they should give us -1, -2, -3, and so on. And if we have those numbers, we will be able to tell A minus 13 should give us -5. Unfortunately, at this point, we cannot do that. Why? Because we have not properly defined what negative numbers are. And how do we do that? Let's just pause for a second. This is actually quite profound concept. Recall we have defined natural numbers and addition, multiplication, subtraction with them. And we know subtraction has a limitation, where the second number being subtracted cannot be larger than the first number, the number being subtracted from. And that's a constraint. And we have seen that in the real world, we want to have a subtraction operation that goes beyond this constraint. 8 minus 13 does have some physical world meaning. It's not something ridiculous. It's something that we really think we should be able to do. But for now, we cannot do that. So, as you will learn in many years ahead, math is just something that we start with a small set of things, then gradually expand our knowledge or understanding of those things. We have those arithmetic with natural numbers as tools. We use those tools to model real problems. 5 plus 3 equals to 8. But when our tools are not sufficient, what can we do? Well, we can do something called generalization. Essentially, we expand from the concepts and tools that we have, try to broaden them, generalize them, make them more useful to new problems. But along this process, it's extremely important to understand that when you try to generalize your tools or broaden their scopes, you don't want to break the old ones. You want to expand those tools in a way that they're consistent with what you have already. In other words, it's not something that you destroy the old thing, then reinvent a new thing, but you, based on what you already have, on top of that, try to expand what you have so that the idea is broader, but is still fully compatible with the older one. So if I have to draw a picture, it's something. Let me get my whiteboard ready. Okay, here's the whiteboard. So, what does that mean? If, let's just say, we have a concept like this. I'm just drawing the rectangle, not perfect. If we want to expand this idea, we did not mean, say, we want to erase this and create a totally new concept. That's not what we are going to do. Because doing that way, we lost all the benefit from the knowledge that we have already labored to develop. How about this green, smaller green rectangle? We cannot take advantage of that. We don't want to do that. what we want to do is to, based on this smaller green rectangle, by expanding it to a larger rectangle, which fully incorporates the smaller one, so that if we talk about this red, the bigger red rectangle, the smaller green rectangle is just a special case of the new bigger rectangle. This is generalization. So this kind of just philosophy is very important in math. A lot of the modern mathematical branches are actually based on this philosophy. And this is actually also true for other sciences. Physics, chemistry, you can observe a simple phenomena, then try to generalize it. Okay? And the generalized situation will include the previous, more specific cases as just special cases. But the two are fully compatible. That's very important. And in computer programming, you will see things like this. For example, if you know object-oriented programming, say C++ or Java or all things, you want to use this kind of idea to build classes of your objects. Okay, all those inherited classes are just of the same concept. So now, how do we introduce negative integers? Remember, what we want to do is that we already know the natural numbers, excluding 0, meaning starting from 1, 1, 2, 3, 4, they are positive, right? So, in that sense, we want to expand our number line for now on the integers, but we want to expand our number line from a half a line, which is like an array, from 0, 1, 2, all rows to the left of the 0. But so far, we have only defined natural numbers. Remember how we define natural number. It's very important to understand such a concept. We define a 0. We define an increment operation that should be the same for all additional natural numbers. With those two important properties, we can add 2, 3, 4, and so on. Of course, we have some other axiom to prevent loops and so on. But the most important things are 0 and the increment operation. With the increment operation, we can easily define what a decrement operation is. However, none of them apply to anything to the left of 0 on the number line, because we haven't defined them yet. We don't know what they are. And as a result, when we do decrement, we cannot go cross 0. We decrement 1 to get 0, but cannot decrement 0. But why we could increment indefinitely to the right on the number line? Because we have an initial point, which is super important, that is 0, right? Once we have that 0, and once we have the increment operation, then we can do all the expansion to the right. So far, if we want to go down to the left of 0, what do we have? Do we need an initial number? No, we don't. We have all the numbers to the right of 0. We can choose any one, say 4 or 5, doesn't matter. As the initial point, the goal is to move to the left. We already have that. Do we have a decrement operation? We already do. Remember, what is a decrement operation? If you have m and mm plus 1, we define decrement m plus 1 equal to m. So we already have a decrement operation available. However, this only applies to 1, 2, 3, 4, not even applies to 0. So our goal is that to take advantage of those two facts. We really think, shall we further extend decrement operation to 0? And what does that mean? The answer is actually yes. It doesn't mean anything until we define what it means. So that means that we want to say, we just want to give this new animal decrement 0 a meaning. What is the meaning of this? We can actually supply a meaning to that. That's exactly actually how we define natural numbers in the first place, right? Remember how we define natural numbers? We just define 1 is increment of 0. We define it that way. We define 1 to be increment 0. And similarly, we define 2 is increment 1. So there's nothing that prevents us from just give decrement 0 a definition. And what should that be? Well, it's another number. And what is that number? It's just a number that we newly defined. However, because of our knowledge, we just won't define this decrement number to be -1. But for now, you should really recognize this -1 is a brand new symbol. Okay? It's just a number, but as we wrote this down, -1 is nothing but a symbol. We could use any symbol, whatever you choose, you like, to represent this symbol. Just like we mentioned that we could choose any symbol to represent 1 or 2. They're nothing but symbols. But we do know this particular number has a connection with the concept of 1. Why is that? Because we are reusing the same decrement operation, and we know this decrement from 0 should be the same thing as decrement from 1. Because 0 is decrement from 1. That's how we define it to be. So, if 0 is decrement from 1, we take a further step, decrement 0, then this is something should be closely related to 1, right? Because we are reusing the same decrement operation that is common for all non-zero natural numbers. It's the same decrement operation. We just need to define it to be something, and that something has a close relationship with 1 because 0 itself is decrement 1. So therefore, we want to take advantage of this knowledge. So we wrote down the symbol as -1. Okay? That's where we should think about how to generalize what we already have. Except there's one small issue. That issue is that because previously we have defined increment and decrement in terms of natural numbers, or as you should know, they are also called positive integers and +0. Now, in order to avoid any confusion, we want to have this decrement problem, say decrement cross 0. We don't really want to immediately reuse this operation decrement per se. What do? Well, we can actually do some cheating. That is that we want to have a new, hey, it's brand new, it's a new operation. But for all those non-zero natural numbers, this new operation is exactly the same as the old existing decrement operation. Then we will go into the negative or the left side of 0 to define additional decrement and what those decrements mean. So that's the trick. We will actually just extending this decrement operation into, well, we still call it decrement, but we use a capitalized D to denote this new operation to indicate that it's a separate, different operation. But nobody can deny that this is strongly related to decrement in this sense. Okay, we define a decrement operation. Look, this is a capitalized D on non-zero natural numbers. That's what we actually defined decrement last time in the, the little d decrement operation last time in the first place. So we are doing exactly the same thing. We just define for those numbers, non-zero natural numbers, 1, 2, 3, 4. The new capitalized decrement operation is exactly the same as the little d decrement operation. Okay? This sounds silly, right? What I'm doing here is just do exactly the same, make a carbon copy. That's exactly what we are doing. But this is not a renaming, meaning that we just did not give a new name to the same thing. No, we create a new thing. This new thing happens to be exactly the same as the older thing. But our goal is not to stop here, because the previous decrement operation only applies to 1, 2, 3, 4. Now the very reason we are doing this is that we have a goal. We want this new thing to expand into something that we have not even know what they are yet. But the reason that they are exactly the same as the little d decrement is just for what I mentioned earlier. We want the new thing to be more general than the older thing, but it's still completely compatible with the older thing. In other words, we don't want to break down what we already have. So this decrement should be exactly the same as the little d decrement as far as all those positive natural numbers 1, 2, 3, 4 are concerned. Now we want to deal with decrement 0, capital D. We don't even try to say what little d decrement 0 is. We don't want to reuse the exact same thing. We just want to expand it into a new thing, but this new thing is compatible with the existing old thing. That way, we can be much clearer about what we are talking about, not to generate any confusion. Okay, so how should we define this decrement thing for numbers that are not 1, 2, 3, 4? Okay, so we got something like this. We want to, on the number line, if we look at all the natural numbers to the right of 0, we got to say 4, decrement to 3, decrement to 2, decrement to 1, and decrement to 0. Notice that this is different from the picture above. Now the decrement operation has a capital D, not a little d. And this is what we just defined, right? We define this to be exactly as this. However, previously, with the little d decrement, once we reach 0, we can go cross that because it's ill-defined. Now, we have not defined yet, but we want to define this decrement operation. It's generalized, it's more broadened, so that it can go cross 0 to a new number, and yet to another new number, and another new number. And this process is almost the same as how we define natural numbers, which grows to the right, right? Now we just want to use the same approach to define a sequence of numbers that on the number line to the left of 0. Okay, so here comes the definition of integers. The common decrement operation on non-zero natural numbers. Notice that here there's a very important adjective here, the common. Because we define the capital decrement to be exactly the same as the little decrement. And we know the little decrement is a common operation on all non-zero natural numbers. Therefore, as of this moment, this capital decrement operation is the same for those non-zero natural numbers, right? They are not a whole group of different ones. They are all exactly the same, single. Even for the capital decrement, it's just still single one. Why? Because the little one is a single one. And we just define this capital decrement to be exactly the same as the little decrement as far as all those positive natural numbers are concerned. So we know at this moment, it's a common decrement operation. Now we just say this decrement operation also operates on 0 and negative integers. Well, what are negative integers? Don't worry, here they are. Where negative integers, -1, -2, -3, -4, so on, are defined as -1, it's defined as this new capital decrement operation on 0. Is this a problem? It's not a problem. It's a definition. So we define -1 to be a big decrement or capitalized decrement on 0. With that, we can recursively continue to the left. So -2 will be defined as this decrement on -1, which we just defined. And the same thing, -3, -4, and so on. Look, this approach is exactly how we define natural numbers. The only difference is that when we talk about natural numbers, we go toward the right on the number line, right? So, with this new definition of negative integers, we want the natural numbers to be kind of put into the big red rectangle. And the natural numbers are our initial smaller green rectangle. So we call those non-zero natural numbers 1, 2, 3, 4, we call them positive integers. And negative integers, 0, and positive integers together, those three things are collectively called, not surprisingly, integers. That's how we define integers. We want to get the negative integers. Now negative integers, 0, and positive integers are all called integers. Okay, 0 is neither positive nor negative. That's for sure. So, essentially, the underlying concept is similar to counting, but we are doing kind of a negative counting down. Okay? But nothing prevents us from to define negative numbers in this way. However, on the number line, they also have a meaning that is this meaning. Okay? So, where you have, because we assume this is exactly the same capital decrement operation on all integers. That's from our definition. So it's not difficult to see the distance on the number line between any two adjacent negative integers, or between -1 and 0, those all must be of uniqueness, which is the distance between 0 and 1. Okay, that's quite obvious. The essence for this fact is that we are using exactly the same decrement operation on all those numbers. Okay, so with that understanding, now we want to think about what can we do with all those new defined integers. Now we know our choices are not limited to natural numbers. We also have negative integers which are to the left of 0 on the number line at our disposal. Okay, so what tools do we need to work with negative integers? Well, just like when we define natural numbers, if we don't have any arithmetical operations, then not very useful. So we want to define arithmetical operations on integers. Okay, so far how many arithmetical operations we have for natural numbers? We have 3. Addition, multiplication, and subtraction. Look, we have not defined division yet. We merely define addition, which is repeated counting, multiplication, which is repeated addition, and we partially define subtraction. It's a defective subtraction in the sense that there's a constraint which cannot allow us to subtract a larger number from a smaller number. And that's actually the very motivation for us to develop negative integers in the first place. So now we are in a position to, at least for subtraction, we want a subtraction that remove that constraint. We want to do subtraction between any two integers, whether it's 3 subtracting 5 or 5 subtracting 3, or 5 subtracting -3, or -3 subtracting 5. We want to do that. Okay? But now, how do we do that? Well, let's talk about, assume what we can do with subtraction. Okay? So here, there's a typo in this slide. Well, that m and m be any integers. Here we have to say n is non-negative. Okay? There's a typo here. I will fix this slide. But this definition essentially is something like this. Okay? If we have a number n which is non-negative to be subtracted from an integer m, we can essentially reuse our earlier subtraction definition. The only thing that we have achieved is now the subtraction operation does not need to have that constraint. So earlier, remember in the previous case when we defined m minus n, where both are natural numbers, but we do have a constraint that n cannot be on the right-hand side of m on the number line. Essentially, what we mean is that n must be smaller than or equal to m. Although we have not formally discussed what this symbol means, but you should understand this merely says that n is a number that is no larger than m. We do have that constraint, but now the new subtraction definition, when n is just positive, it defined almost the same way. M subtracting 1, it's always decrement from m. And now there's no constraint because m could be a negative number in the first place. Okay, so the only thing now is n needs to be a non-negative. We have not discussed what, say, 5 minus negative 3 means. So this definition does not work that. So for now, we want our, this slide has some problem, but I will fix it. But this number for now needs to be non-negative, meaning it's a natural number. Okay? So with that understanding, m minus 1 is just like what we did last time. It's decrement from m. Okay? So earlier we said that we decrement m plus 1 equals to m, but essentially that's the same thing because now we say decrement m is m minus 1. Okay, so if that's the case, we continue what we did last time. M minus n is just subtracting 1 or decrement from m n times, where n is a non-negative integer. It could be 0. If m subtracting 0, it's just nothing. Nothing happens. So m minus 0 is always m. That is understood. So that means that in this case, the decrement operation is fully working on the number line. Previously, we said that it was very clear. Earlier, there was a boundary problem. We cannot go across this 0. Now, we don't have that constraint. We can freely decrement. Remember, now it's a different decrement. It's a capital D decrement. We can freely go across 0. Okay? That way, we can see that on the number line, whenever we subtract a number, a natural number from an integer, it's essentially the same thing as what we did earlier. We just count down. But now it's a new decrement which allows us to go across 0. Okay? So that way you can clearly understand now what is, for example, a minus 13. That's the question we have last time. So what is a minus 13? Essentially, you start at a on the number line. You perform this new decrement d 13 times. Remember, as long as you are still in the natural number position, the decrement, big decrement, is exactly the same as the little decrement. Therefore, we don't have any problem of incompatibility. This decrement or subtraction is fully compatible with our earlier constrained subtraction. That was just a special case of the new integer subtraction operation that we talk about. Okay, so that's how we solve this problem. And we want to investigate, say, things like, what does this mean? That will be for the next lecture. But today, we want to really understand that this is nothing but a generalization of what we have of the natural numbers. Okay? So it's just very straightforward way to think about what happens when you subtract a large number from a large natural number from a smaller natural number. Further, if we have things like -5, what is -5? It's decrement 5 times from 0. And that's our starting point. What is -5 minus 13? You continue to decrement 13 times from -5, and you should be able to see that is -18. Still, we have not defined what this means. Okay? So this will be for the next lecture, but for today, we want to quickly see if we want to do this for integer additions, where the second integer is being added is again a natural number, how that works. Okay? So okay. The increment operation. Look, now we want to introduce the inverse of the new capital D decrement operation. Previously, we defined the little d decrement operation as the inverse of the little I increment operation, right? Because easily on the number line, if you have an integer m and you have its next natural numbers on the number line, which is essentially increment m. So clearly you see this is increment, this is decrement. And the decrement is just the inverse of the increment. We can actually define a capital I increment following exactly the same idea. It's interesting now with the capital increment, decrement, we first define decrement. Then as inverse, we define increment. But for the little I, we define increment first and define decrement. It's not really just that interesting because we know now they are just inverse to each other. So therefore, we now are ready to define the increment operation on integers. This is very important because the very purpose we want to introduce those capitalized operations, increment or decrement, is because we want to expand their client or their customers from natural numbers to integers. So therefore, for any integer m, now remember m is just integer, it could be negative. So any number on this number line, -1, -2, -3, any number. Doesn't matter whether it's a positive number or negative number. Let's just say any number. An increment operation on m minus 1. So now we have already defined decrement and what is m minus 1. 1 is a natural number. We know what is m minus 1. M minus 1 is nothing but decrement on m. So the increment defined on a number's decrement, we first get the decrement of this integer so chosen, which give us -2. And then we perform the big increment on this number 2. And remarkably, I'm just joking, not surprisingly, this is -1, right? So increment m minus 1 is nothing but m itself. Does that make sense? Because we define decrement, the big decrement for all integers. Therefore, our increment definition should must rely on this fact that m minus 1 now applies to any integer m. M doesn't have to be a natural number that is at least as large as 1. M can be any integers, and this is well defined. So for any integer, we have already defined what its decrement is. And this new increment operation should be just operating on that already decrement 1. And it should give us right back at the number we start with, which is m. And that is what this definition all about. It's very important to emphasize that at this point, you should recognize, you can verify that this new increment, if it's on a natural number, which means from 0 to 1, is exactly the same as little increment of 0. And this can be rigorously proved. And the proof is very simple. And we just want to show that. So what is increment of m in the first place? Well, look at the definition. This is an increment m. We know there's a number m where decrement n is m, right? Essentially, this is m plus 1. But n is equal to m plus 1. But remember, we have not formally defined subtract or addition yet. Now we are talking about integers addition, not natural numbers addition. And we assume m is just any integer. So therefore, m plus 1, for m being an integer, we have not formally defined what that is. Okay? But we do know decrement of n, what that is. So that's exactly why we want to define this increment in the first place, to allow us to have this addition operation. So we start with some number that is technically we don't know what it is as m plus 1. We just call it n. But we do know if we decrement n, we will get m, right? If we decrement n, we'll get m. And now, because of this, increment m will give us right back at m. Okay? So that's what this is. Now, if you think about if m, we are trying to show that if m is actually a natural number, meaning that it could be 0 or 1 or 2, then this should be equal to increment, little increment. Don't get confused. I hope you are still with me. But this is very obvious. Why? If m is a natural number, we can easily show n must be n plus 1. Now this n plus 1, I should write it in red to show that, remember now we are assuming m is a natural number. Therefore, m must be n plus 1, right? Because the decrement of n equals to m, and we know m is itself is a natural number, so this m must be n plus 1, because now m is a natural number. And the only other natural number that have a decrement operation and resulting in m is n plus 1. So therefore, we know this is n plus 1, and therefore this is increment m. So this is very trivial, but logically you need to see why this is true. That when we so define this capital I increment on all integers, this is well defined through the decrement operation, then this definition must be completely compatible with the increment operation, little I increment operation that we have already defined on the portions of the integer that are called natural numbers. In other words, now we just show that this increment m equals increment m if m is a natural number. This is important to understand. It's easy to, I think my YouTube video has some problems, but looks like the bandwidth has some problem. I hope the live streaming is still going on. Let me see my internet speed. I do have good internet speed, so I hope you guys are listening to me okay. So that's very important. Now we have an increment operation that is fully compatible with our previous increment definition, which was only on natural numbers. Now we have increment operation for anything, any integer. Okay, so now we have properly defined both the increment and decrement. Remember, the difference is those two new operations are for any integer, not just for natural numbers. So it won't be surprising if we tell you that we can do that for addition, where the first number is any integer, while the second integer is any natural number. Okay, so this is the addition of integers. Once again, I'm sorry, there's a typo here. I should say n is a natural number. So m is any integer, while n is any natural number. Then this addition, m plus n, is defined as m plus 1. It's just this new increment m, because now this increment, capitalized increment, will work for any integer m. Whether it's positive or negative, it doesn't matter, because we can always define this as plus 1, m plus 1. And with this definition, we can further define m plus n. Notice the first number m here is any integer, while the second number here n is a natural number. We can define exactly this way. Okay, but we have, with this definition, we will be able to answer what is 5 plus 3, what is negative 5 plus 3, and so on. But we have not answered what is 5 plus negative 2, or what is negative 5 plus negative 2. We have not defined what row sin yet. So with the subtraction and addition that we take a look, m plus n or m minus n, it's important to understand m is any integer. While n is natural number. Okay, so next lecture we will expand our definition of the subtraction and the addition to answer questions like what is this or what is this. Okay, number line will be hugely helpful to understand such things. Actually, for young students, this is, I believe, in middle school topic, but for 5th grade, to understand those things at a very kind of just a deep level is important. Not just you can have a way to memorize those things, but you cannot really just say, just mechanically understand it, but without really understanding it. Okay? Okay, that's it for today. I hope that I will give you some homework on this. I hope you understand that what we talk about today is very deep in terms of, from a philosophical point of view, we generalize something that has a constraint. By generalizing, we remove that constraint. But the new version of the generalized the tool must be compatible, fully compatible with the old one. It cannot break the previous one. Therefore, we are making the tools more useful. We did not break down the original tools. We merely make it a more general one so that it can be more useful. This kind of concept is very important in mathematical study. In your future study, you will see this type of ideas again and again and again. All right? I will see you next lecture on Friday. Bye.